Magnetic dipole moment of a current loop is denoted by M vector. It is a magnetic dipole moment. Galvanometer is a device which is generally used to detect the amount of current in any circuit. This quantity NAB divided by K is constant for a galvanometer. Except the current element, the rest of the things what we have in our RHS are constant for galvanometer. Hello everyone, welcome to session 4 of chapter 4 Moving Charges and Magnetism. This is Swati from Department of Physics, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. We all generally know about what is a torque. It is a force which helps in rotating a body. So let us now understand what is a torque on a current loop magnetic dipole. So magnetic dipole moment of a current loop is denoted by M vector. It is a magnetic dipole moment. We all know electric dipole moment, it is P vector, but magnetic dipole moment we are discussing now, so it is M vector. What is magnetic dipole moment? The magnetic dipole moment of a current loop is defined as the product of current and the area vector. So magnetic dipole moment is M vector. It is defined as the product of current and the area vector A of the loop. We know if a loop is having area vector that is A, so it is given as M vector is equal to I into A vector. Suppose if a loop has n number of turns, then the dipole moment M is equal to n number of turns into product of current into area vector. What is the SI unit of magnetic dipole moment? We know the SI unit of current is ampere and area it is meter square. So it is ampere meter square, the SI unit of magnetic dipole moment. So this magnetic dipole moment helps us in understanding a torque in a current loop. So let us now derive an expression for torque in a current loop. For that, I will consider a rectangular loop which is placed in uniform magnetic field. This is north and south pole of magnets which provides a uniform magnetic field. So I'll consider a rectangular loop A, B, C and D. I'll take this side as A and here it is B. Now this coil is connected to a source. If I divide this length of A into two equal parts, my distance here till midpoint is A by 2 and here it is A by 2. So this is a rectangular loop which is placed in uniform magnetic field. Now let us say that the magnetic field is in this direction. So it does not exert any sort of force on the arms BC and AD. Why it is so? Because the arms of this coil BC and AD are parallel to magnetic field. So when they are parallel to magnetic field, theta will be equal to 0. We know, suppose if it is a current carrying conductor, this is a current carrying conductor, a coil. So force due to a current carrying conductor, we know the expression, it is F is equal to ILB sin theta, where I is the current, L is length of the coil and B is the magnetic field. So here theta is equal to 0 because BC and AD are parallel to magnetic fields. Now what happens if the theta value is 0 substituted in the equation? We will get the force is equal to 0 and hence the magnetic field does not exert any force on the arms BC and AD. So let us learn in detail about this. So I have considered ABCD, a rectangular loop which is placed in magnetic field B. So the force exerts on arms BC and AD are 0 because they are parallel to the magnetic field. So what about the forces on the arms AB and CD? Let us substitute the value in this expression. We get F1, I'll consider it for AB. It is equal to, we have ILB sin theta. Now theta value is equal to 90 degree and we get F1 is equal to ILB. But what is this L? That is length of the arm. That is nothing but small b. So I get the expression IB into B. So I'll take it as F1. Let us similarly apply the same thing to this arm, that is CD. So again it is having a length B. So we get the same expression, that is F2 is equal to IB into B. So from this we'll get to know that F1 is equal to F2. So these two forces are equal in magnitude but they are opposite in direction. Therefore, the net force on the loop is 0. But there exists a torque. So what is this torque due to? This torque is due to a pair of forces. So generally how to find the torque? The torque is generally calculated as tau is equal to the magnitude of either of the forces, that is, I'll take it as F1 into the perpendicular distance. What is this perpendicular distance? We have a perpendicular distance to this side, that is a by 2, which means the sum of a by 2 and a by 2 gives us a. Let us substitute, that is tau is equal to f into a divided by 2 plus a divided by 2, or tau is equal to f into a. But what is f? It is tau is equal to, I'll substitute the magnitude of either of the forces, that is IB into B into A. What is small b? It is the length, and what is A? It is the width of a coil. So length into breadth gives us area. So our expression becomes tau is equal to, in the place of B into A, I can substitute area term, that is IAB. So the expression for torque on a current loop in a magnetic field is given by tau is equal to IAB. Suppose if the coil is having n number of turns, then tau is equal to NIAB is the expression for torque on a current loop. Now let us study about the next topic, that is a moving coil galvanometer. Before going to understand the mechanism and the working of galvanometer, let us understand what is a galvanometer. What is this device used for? Galvanometer is a device which is generally used to detect the amount of current in any circuit. So it is a current sensitive instrument so that it can even detect a very little bit amount of current which is flowing in a circuit, which means it can even detect a small amount of electric current. This is how the galvanometer fabrication is. So we can see here there is a soft iron core in between, and we have magnetic fields or permanent magnets, that is North Pole and South Pole. We do have a pointer in the galvanometer. We generally see the pointer which shows us the reading. So this is the scale where we used to read the readings of galvanometer. Generally we use in a lab. So the pointer is here, and this is a coil. You can see here there is a pivot inside the coil. So this coil is located between the two poles of magnets, and here with the help of magnets we can observe there is a uniform radial magnetic field. So this is the basic diagrammatical representation of the fabrication of galvanometer. Let us now study the principle of galvanometer, which is very important. When a current carrying element or when a current carrying coil is placed in a uniform magnetic field, it experiences a torque, it experiences a kind of force such that the current passed in it is directly proportional to the deflection produced, because I told you already that is galvanometer is used to detect the amount of current. As soon as we see the deflection in the galvanometer, so we can conclude that so much amount of current which is flowing through the circuit. So let us study about the construction. A galvanometer consists of a coil with many turns which is free to rotate about its fixed axis in uniform magnetic field as shown here already. There is a cylindrical soft iron core here in between, which not only makes the field radial but also increases the strength of the magnetic field. You can see here, because of this uniform radial magnetic field, the cylindrical coil also strengthens the magnetic field here. So when a current flows through the coil, the torque acts on it immediately. What is the theory behind the moving coil galvanometer? So the expression of torque, this torque tends to rotate the coil. So we know the expression for torque acting on a rectangular loop keeping in uniform magnetic field, that is just now we derived, that is tau is equal to NIAB, where I is a current, A is an area element, N is number of turns of a coil, B is a magnetic field. So this magnetic torque tends to rotate the coil of a galvanometer. As a result of this rotation, the spring here, SP, it provides anti-torque, or we can say that the restoring torque. What is restoring torque is denoted by, it is K phi. So this restoring torque balances the magnetic torque. Usually the magnetic torque will tend to rotate the coil, and inside the coil SP, it generates an anti-torque so that the coil will be balanced with the magnetic torque and it will maintain a steady angular deflection. So it will reach an equilibrium position because it gets balances. So at equilibrium we know K phi, that is an anti-torque, or we can say restoring torque developed by a coil, which is equal to the magnetic torque of a rectangular coil which is placed in a magnetic field, that is NIAB. So in this expression, K is the torsional constant and phi is the restoring torque per unit twist. So from this expression we can write phi is equal to NABI divided by K. So this quantity NAB divided by K is constant for a galvanometer, except the current element. The rest of the things what we have in RHS are constant for galvanometer. So from this we can write phi is proportional to NAB divided by K, which means it is directly proportional to number of turns, area and magnetic field, and it is inversely proportional to the torsional constant. So in this expression, phi divided by I is called as deflection per unit current, and we will call it as current sensitivity of galvanometer. What is the deflection that we can observe per unit time says us about the current sensitivity of galvanometer. So from this expression we can write the current sensitivity phi by I is equal to NAB divided by K. So which clearly says about the current sensitivity depends upon number of turns, which means it increases by increasing the number of turns, and current sensitivity increases by increasing the area element, and current sensitivity increases by increasing the amount or the intensity of magnetic field. So we are talking about the moving coil galvanometer. The galvanometer cannot be used as ammeter. There is a difference between the ammeter and galvanometer. So galvanometer cannot be used as an ammeter because ammeter is a device which is used to measure the current, but galvanometer is a device, it is a sensitive device which is used to detect even a small order of current. It can even detect an order of microamperes current in any circuit. So these are the advantages of galvanometer and the theory, principle and working of galvanometer. Let us now understand how can this galvanometer can be converted into an ammeter. So our next topic is conversion of galvanometer into ammeter. A galvanometer can be converted into ammeter by connecting a low resistance in parallel, which means suppose I have a galvanometer here in any circuit, I can connect a low resistance, or we'll call it as a shunt resistance in parallel to it. So we can say that the galvanometer can be successfully converted into an ammeter. So here I have shown how the galvanometer and the shunt resistance can be connected in parallel. So we can say that the potential difference across S, which means V across S is equal to potential difference across galvanometer. So from Ohm's law we know V is equal to I into R. So in this expression, so the potential difference across S, that is V across shunt, is equal to the potential difference across galvanometer. But what is V? According to Ohm's law, it is I into R. R is nothing but the resistance. But how to find the current across the shunt resistance? Here it is Ig, current across the galvanometer. This is the total current flowing to the circuit. So this must be obviously I minus Ig, which is the current passing through the shunt resistance. So the current I, in the place of I have to write I minus Ig, and in the place of R, resistance here is a shunt. So it is I minus Ig into S, which is equal to Ig is the current flowing through the resistance of galvanometer G. So I can write it as Ig into G. So here we have to find the expression for shunt resistance. How to find the value of shunt resistance? For that I have retained S to the LHS and writing remaining terms to the RHS, we get shunt resistance S is equal to Ig into G divided by I minus Ig, which means the shunt resistance or a low resistance can be calculated with the help of this formula. Similarly, how can this galvanometer can be converted to an voltmeter successfully? So galvanometer can be converted to a voltmeter by connecting high resistance in series with it. So when the galvanometer is connected to a high resistance in series, we can say we can convert the galvanometer into voltmeter successfully. Now let us find what is the calculation of R, how to find the value of this high resistance. We know from Ohm's law we have the expression V is equal to I into R. So what is the current here? It is flowing across the galvanometer, so it is Ig. So in the place of I have to write V is equal to Ig into R is the total resistance in the circuit. So I have a high resistance plus the resistance of galvanometer. So it is G plus R. Or we can write it as G plus R is equal to V divided by Ig. We need a value of R. So R is equal to V by Ig minus G. That is the resistance of galvanometer. So knowing the values of V, Ig and the value of resistance of galvanometer, we can calculate the value of this high resistance that has to be connected with galvanometer to convert that into voltmeter. So now we came to know what is a current sensitivity, what is a moving coil galvanometer. We have understood how can the galvanometer can be converted into ammeter and voltmeter. Let us now understand another important topic, that is voltage sensitivity of a galvanometer. So what is voltage sensitivity of a galvanometer? It is defined as deflection per unit voltage, where current sensitivity is deflection per unit current. Here it is voltage sensitivity, deflection per unit voltage. If V is the potential difference across the galvanometer and I is current through the galvanometer, R is its resistance, then voltage sensitivity is denoted by deflection per unit voltage, that is phi by V, which is equal to, according to Ohm's law, we know V is equal to IR, so we can write it as phi divided by I into R or R into I. But we have defined what is phi by I. It is current sensitivity. We know that phi by I is equal to NAB divided by K. So our equation becomes NAB divided by K into 1 divided by R. So voltage sensitivity is nothing but current sensitivity divided by resistance. So in today's session, we have learnt about the torque on a rectangular coil loop. And also we have learnt about moving coil galvanometer, how the galvanometer can be converted into an ammeter and a voltmeter successfully. And also we have learnt about the current sensitivity and voltage sensitivity of a galvanometer. In the next session, we'll come up with some more interesting topics. Until then, keep learning all of you. See you all in the next session. Thank you.